for radio frequency identification. It's used all over the place, from parking passes on campus to retailer security to driver's licenses in some cases, pet tracking chips. It's all over the place. And what it does, well, the one in the book is EPC, which stands for Electronic Product Code. It's a more advanced barcode, which can hold more information and can be readable from a range of up to 10 meters or a little over 30 feet. And the system, it's got a reader and a tag. The reader is constantly sending out a signal, and the tag, which is essentially a sticker with a small antenna on it, can either reflect that signal back or just absorb it. If it reflects it back, it will add on a little code called an RN16, which is just a 16-bit random code. And it's because RFID uses slotted aloha, so instead of sending the actual thing that the reader's asking for, because collisions could make it very expensive as those are very long, it sends in this to kind of reserve a slot, and then when a slot is found, the RFID reader sends back that RN16 with a little extra stuff on it as an acknowledgement, and then the tag sends its identifier, and once the identifier is sent, the tag stops sending so that other tags around can send theirs. The reader can also adjust the range of slots if there are too many or too few in the area to save on power. And the one in the book, it's a Class 1 Gen 2 EPC system. There are different classes and different generations, and there's a lot of differences between them. And RFID, the tag uses a very simple form of modulation, which makes it so that it uses very little power and is very cost effective to mass produce. But it's still a bit more costly than just slapping a barcode on something. And next, we've got data link layer switching.
Okay, so that was RFID or RFID, as I like to call it. I think that's what most normal people call it. Anyways, I want to talk about data link layer switching. So we have bridges that connect multiple LANs together, essentially. And by joining these LANs together, you can get more capacity than just a single landline. It's important that you make sure the data is not sent on any ports which are not needed. A lot of times, you can kind of figure out where a message needs to be sent, so you don't need to flood the whole network. So there's two algorithms that can be used to create a bridge. The first is backwards learning, and the second is a spanning tree. And so let me just talk a little bit about backwards learning. So there's three rules that basically a learning bridge will have. It's that if the port for the destination address is the same as the source port, discard the frame. So essentially, if you are sending your frame to something which is on the same port as your bridge, do not send it to all the other ports, because it's already going to be spread to that same port. The second rule is that if the port for the destination address is the same as in the source port are different, then forward the frame to the destination port. So basically, if you already know where the message is going, just send it to that port. And the last one, if you don't know where the message is going, just forward it to everybody. The way this ends up looking is essentially, if you send a message from B5 to say B2, you're not going to send it among all these other branches if all these bridges know where it's at. That's basically what that rule is saying. And so then there's the second idea, which is spanning bridges. So basically, you don't want to create a loop, because when you have a loop like this, see how all these bridges are connected and it creates a circle? You're going to end up having an infinite loop of just forwarding packages around. So if you send a frame to a bridge and doesn't know where that destination is, it forwards it to everybody to just make sure someone gets it, right? So say you have frame A right here. You have, it starts at A, and you're sending frame, right? This frame 0. So it comes right here. And B1 doesn't know where it's going, so it's going to forward it to everybody. And you see, now you have these two frames coming on these lines. B2 doesn't know where it's going either, so it forwards it back this way, and it keeps going on forever. So essentially, the solution to this problem is you create a spanning tree, where essentially these two connections right here become, they're almost discarded. Even though they're actually connected in real life, you create a minimum spanning tree. So that way, once you have a root bridge, there's only one possible path to everything, so you can't have it going back and forth infinitely. And I think the better way to explain this, because it's a bit hard to explain, is through the demo that we did. So I went ahead and cooked up a little something. Let's see where it's at. Here we go. I hope you guys can see this. So essentially, here's a very basic idea of what a single learning bridge would look like. So here you have it in the middle, and you have two different landlines on the sides. And we have a funny representation of like a message that you guys might appreciate. So say A is going to send to C, right? Which is on the same landline, right? So it doesn't need to go to this side. But the problem is when B1, this bridge, gets the message, it doesn't know where C is currently. And so it's just going to flood it to everybody. So as you'll see, our good old friend Nick Cage goes there and both sides. Because the reason it got forwarded to this side is because B1 doesn't know where C is. So now, say for instance, we're going to send C to A. B1 just got a message from A, if you remember, right? It just had someone pass through there, so now it knows where A is. So when C is going to send to A, it's not going to forward it to everybody else because it knows where that is. And a bit more of a complex example is we're going to have something like this. And here you have two different learning bridges, right? And so this is actually one of the problems you end up doing in the book. So if A sends to C, right? Right here, even though it's on the same connection to the bridge, right? It's got to forward it to everybody else because the bridges don't know where they're at yet. If E sends to F, the same thing's going to happen. It's going to forward to everybody else. When F sends to E, now here's the interesting part. When F sends to E, right? E had just sent a package, right? And it hit B2. So B2 knows where E's at now. So when F is going to send this message, the hub right here is going to send it to everybody. But when B2 gets it, it now knows where E's at. So it's not going to forward it to anybody else. So right here, you'll see it'll stop right there. And so essentially what this does is it basically makes it so you don't have to flood the entire network whenever you want to send something. I'll show you the rest of them. So here it already knows where E's at, so it goes directly to it. D's going to send to A, goes directly to it. And this one's a bit more interesting because it knows where F is at. B2 knows where F is at, but B1 doesn't. So you'll see you kind of have an interesting behavior there. So you see there, I had to send it to A and C because B1 had no idea where it was at, but this bridge did. So that's basically the idea of a learning bridge right there. And I believe that's it, so I think questions.
Is learning bridges in